In this video, we're going to discuss bit patterns, bytes, hexadecimal numbers, and ASCII codes. Bit is a fundamental unit of memory, and entire memory locations are comprised of sequences of zeros and ones. Bit is a binary digit, and that means that it can store only 0 or 1. So everything on a computer is stored in combinations of these bits. The units of storage could differ in sizes, which would correspond to different types of data in computer memory, but every single addressable unit or accessible unit of storage accessible in computer memory is made out of bits. There are some other units of measurement where the bits are used. For instance, a unit of bits per second used to measure internet bandwidth. Byte is a quite popular reference to a memory location size, and it's normally equivalent to a combination of 8 bits. There's also a reference to it known as octet, because it's octal combination. So this is an example of a byte with some sort of bit pattern stored in it. Also should be notable that in Latin character encodings, 1 byte normally corresponds to storage of a single character. You can convert a binary number stored in any memory location by simply multiplying the value of 0 or 1 by a power of 2, where the power indicator corresponds to the position of the bit in this combination of bits. The bit positions are numbered 0, 1, 2, 3, 4, 5, 6, 7, and so forth if you have a larger bit pattern. Therefore, we count bit positions from right to left, and we start with position 0. So therefore, 2 raised to the 0th power will equal 1. This is how we get this 1. And then we can multiply the value of this bit, 0 or 1, by 1, which means it's just taken literally 0 or 1. The next bit is at position 1, and so 2 raised to the first power is 2. So therefore this 1 contributes 1 multiplied by 2 to the final result, and so forth. So this is 2 raised to the second power, to the third power, to the fourth power, and so forth. This is 2 raised to the 7th power, which is 128. And you simply take the values of these bits and multiply by these powers of 2, and you sum up everything here, and you get your final result. So this specific bit pattern corresponds to the decimal value 42. There's also another term that is used not very often, but it does exist. A nibble represents a half of a byte, which is just 4 bits. So this is merely for a convenience to reference 4 bits of storage. A hexadecimal notation is used to simplify bit pattern notation. So you can see that even using a 4-bit pattern could be quite difficult to distinguish by human eye from one pattern to another. They all pretty much look alike. So a better choice is to record these bit patterns as a single digit. Of course, from 0 to 9, these are all decimal digits, but then it would still be inconvenient if we continued to use decimal notation to encode these remaining bit patterns right here. So a decision in hexadecimal notation is to replace the missing digits with characters A, B, C, D, E, and F. So from 0 to F, these are all 16 unique hexadecimal digits, and each single one of them represents this specific bit pattern. So that's just a pure convenience of recording bit patterns as hexadecimal numbers. For instance, if I want to take a combination of A, hexadecimal A, then hexadecimal C, like this, then say 3 and 1, you can see that if I use this just as a bit pattern using binary notation, this is hard to distinguish even with spaces here inserted for reasons of readability. So it's a much better choice to take this combination of 1010, which is an A, and record it like this, and then take C instead of writing down a binary number here, and 3, and this is of course a 1. So this could be recorded as hexadecimal AC31 as opposed to this binary equivalent, and without spaces it becomes really difficult. If we double the size of the data type, you can see that here even more. You see that this notation is much clearer than this. Of course, if you need to go from the existing hexadecimal value back to the original binary equivalent, you just have to take each individual digit and replace it by its 4-bit equivalent using table just like this. It's a pretty straightforward replacement of each digit by 3 corresponding binary values, just like this, right? So this 3 corresponds to this value, and this 1 corresponds to this binary value, and then this next 4 bits corresponds to this C, and so forth. So you can pretty quickly convert from hex to binary and from binary back to hex by just using this correspondence right here. In programming languages like C and C++, also Java and C#, hexadecimal notation, just like this, has to be recognized by compiler. So we use a prefix in front of this number. So if I want to write down this number inside the program, I would have to use this notation. You need to use 0x prefix. Everything here could be legally written as lowercase or altogether as uppercase. It doesn't matter. All of this will be recognized likewise as a hexadecimal number. And of course, I mean, you should probably follow a specific style. I think that this is quite popular to use uppercase characters for hexadecimal numbers, and then use 0x as a lowercase. So here, if I want to say integer x equals this number, this will encode, you can see this will encode altogether 8 hexadecimal digits multiplied by 4 bits. This will encode a 32-bit number in computer memory. You should also not use casually leading 0 in your code in situations such as this. A compiler will interpret this 34 as an octal number. Octal numbers correspond to bit patterns comprised of 3 bits. So in octal or base 8 numbering system, there are only 8 digits ranging from 0 to 7. So for instance, digit 8 here would be an illegal digit because compiler will interpret this number with the leading 0 as an octal number. So this is an illegal digit here. The legal range for octal numbers is ranging from 0 to 7, limited in this range. And so if I go back to my original version of it, which is now legal, this simply represents bit patterns 0, 1, 1, which corresponds to 3, and 1, 0, 0, which corresponds to digit 4. But we're taking only 3 bits out of this, and you can see in this range from 0 to 7, the first bit here is 0, so we can totally ignore it, and octal notation helps us to encode these combinations of 3 bits. So this would be a binary equivalent of this octal number. Just be aware of it and don't use. So this is a decimal 34 and this is an octal 34. Now to quickly convert between all of these notations or base 16, base 8 and base 10, and also binary base 2, you can use a calculator. So this is Windows 10 desktop calculator. You'd normally switch from the standard view to a programmer view, and then typically you just want to recognize the data type that you're working with. For example, if this we already decided that our integers may be a 32-bit size, then we would want to switch to this binary view perhaps and switch to double word. Double word on Intel architecture corresponds to 32-bit size. You can see that these are all the bits that correspond to 32-bit size value in memory. So now if we want to try this right here, we could indicate that we want to enter hexadecimal number, switch here, and I can just copy and paste by Control-C and Control-V into this calculator. You can see that I get my binary equivalent right here. I will try to press Control-C to copy it over, and so this is the equivalent that the calculator just gave me, and of course you see that this is exactly to the same numbers, but this number we put together manually, and this is the one that the calculator gave us. Both are equivalent. Likewise, let's clear this, and if we want to try this octal version right here, we switched on octal notation and we can enter 34, and now we can switch over to the binary equivalent here. Again, press Control-C and paste this in, and you see that this is again exactly equivalent, but the calculator just chops off the leading 0 off of here, so this would be a 0 anyways, 0 or non-zero, whichever notation. This is the answer from the calculator. our next slide here talks about 2's complement integers. 2's complement integers is the type of encoding used in all modern computers to encode both positive and negative values. So, for instance, here we use an example of 1 byte, which is 8-bit in size, and we encode 0 simply as a combination of all zeros. Then we say, let's encode a 1, and we just add 1 at the lowest bit position, and this would encode a positive 1. And likewise, we can go through all combination of bits. For instance, if I want to try here to encode decimal 2, I would go from binary 1 to binary 10, right? So this would be the next encoding. If I had 2 in this table, then 2 would look like this right here, just simply with the 1 in the second position and 0 in the lowest position. And then, of course, if I want to encode 3, that would look like this. I just take this number and see where I can fit the next one. So it fits right here. Then if we want to go to decimal 4, then we take the prior number, and we realize that we already kind of like ran out of space over here, so we replace these 2 digits by 1 and add 1, just like we would do in decimal system with all 10 digits available to us. So, and this would just continue over here all the way down to the highest number, 127. That can be a positive encoding, and this would correspond to 0, 1, 0, 1, 1, 1, and 1, 1, 1, 1, right? So these 8 bits, and so we have this value in our table. In 2's complement integers, the highest bit is interpreted as sign bit. If this bit is set to 1, it means that the number is a negative number. For example, you see that in this simple rotation of bits of the encoding, if we take this value and we try to use it as use the next combination, which is simply all zeros over here and a 1 right here, right? So this would be sequentially next possible combination of zeros and ones compared to this. So this for sure should be interpreted as a negative number. Okay, so this is a negative number. So what is this number? We haven't determined yet, but this number is a negative number simply because the first bit indicates a 1. So 0 represents a positive value like in all of these, and 1 represents a negative number. Now, to be able to encode negative numbers, the idea behind it is that there are basically 2 steps to follow. Let's use an example of 1 right here. So positive 1, of course, looks like this. All zeros and 1 at the end. So if we take 1 and we want to find out what is a negative 1, so we try to find out what negative 1 looks like. There are 2 steps to follow. Step number 1 is to flip all bits, and this of course is Simple thing to do, so we just flip all these bits, they become all ones, and this becomes a 0. And in step number 2 we add 1. So this would be quite easy to add 1 right here, so just replace this 1 with the 0. So after executing these 2 steps, we get a -1. And you can see that this is why -1 occupies the lowest part of this table, because it's just like all the negative numbers. If you follow these 2 steps, taking a positive equivalent, flipping all bits and adding 1, you'll realize that you will be encoding these binary combinations, indicating, of course, negative numbers, but they all will be stored here backwards, going from -1, -2, -3, and all the way to -128. A 0, of course, is occupying the top position, and all bits are set to 0. So this is the 2's complement encoding of all numbers. Of course, if you look at the binary pattern here, you'll realize that we can also write it as a hexadecimal value FF. So if you see quantities of these hexadecimal values in computer memory dumps, or looking at blocks of information, binary blocks of information written somewhere in the structure of a file system, and you'll see patterns of hexadecimal F values somewhere, just recognize that these are all -1 negative values. This 2's complement encoding has this property that if you, for example, increase the number of bits by like making it twice as much, so this would be FF hexadecimal, it still doesn't change the idea of 2's complement integer. In fact, this would be still a -1. This would still be a -1, just like before. The number of digits does not affect the value, because if we use the same steps and flip all bits here, they will all become 0, and if we add 1, we will have 0, 0, 0, 1, which is, of course, is a 1. So you see that this -1 can be converted back to +1, and of course similarly this +1 can still be converted to a negative equivalent by flipping all bits and adding 1, and therefore this and this both represent a -1. So this is similar to like in the positive range. If I want to in the positive range, if I want to do something like this, right, add another bunch of zeros in front of it, this will not change the value of my number, right? So adding leading zeros to positive number doesn't change anything. Likewise, adding a 1, like extending the sign bit, does not change the value of a negative number. So if we go from a byte to a 2-byte sized integer, nothing changes here. It remains -1. So these are all proper. So by the way, this operation of taking the sign bit and extending it to the left is called, this operation is called sign extension. Okay, so this is sign extension operation, where you basically take your original sign bit, which is right here, 4 and 4. This is your sign bit right here, and you will be extending it down this way, just like this. So this is your information about 2's complement integers, and our next slide gives you an example of a positive 13, which is encoded as 01101, and we use this 5-bit example of a bit equivalent, binary equivalent of 13. And so these are the steps: flip all bits and then add 1, and this is a negative equivalent, and you can see that it the same set of steps is applied to a negative 13, which is this, and then we invert each bit or flip each bit and add 1, and we end up exactly with what we have started with. So 13 becomes minus 13, and then minus 13 becomes again 13 by using the algorithm of this 2's complement encoding. It's just an example of what we've discussed before here using -1. ASCII characters is the type of encoding that is used in modern encodings of characters, and ASCII stands for American Standard Code for Information Interchange, and it is simply put a combination of encodings that represent printable characters. The first 32 characters, ranging from 0 to 31, represent control characters. Among them you will find escape, which is decimal 27, or carriage return, which is decimal 13, or line feed, which is a decimal 10. And here is decimal 9, which is horizontal tab. And all printable characters begin with space, which is encoded as 32, decimal 32. In this table, we show that ASCII encodings of printable characters can be effectively represented by 2 hexadecimal digits, from 0 to 7 right here at the top, and right here from 0 to F. So for instance, uppercase B would be represented by a hexadecimal version 42, and lowercase b would be 62. So this is the choices here, and of course you can see that there are some punctuation characters at the beginning of this printable part of the ASCII table, and of course also digits. So digits actually range from hexadecimal 30 to hexadecimal 39, from 0 to 9. So these are conventional digits. So here we have a link to interactive ASCII decoder if you'd like to convert characters and their equivalents of encodings. But I also would like to show you that this file that I have opened in Visual Studio, which is called notes.txt, if I copy full path and close it and go to File and say Open File, and this is the file right here. But in Visual Studio there's a tool right here that you can say Open With, and it gives you some choices. One possibility is to open it with a binary editor and click OK like this. Let me resize it to make it perhaps a little bit more visible. But this is the same file that I opened in Visual Studio. I cannot update the size of the font here, but you can see that now this is what I've been typing in our today's presentation, and here's the dump of every ASCII code that I've used in this file. So this is now called a binary editor, and many different applications do include some capability of showing hexadecimal values like this, and even allow you to change it. Very recognizable pattern is 0D0A, which is carriage return and line feed, and this is a new line encoding on Microsoft Windows. So again, this was achieved by going to File, Open, File, and using open with and binary editor.